Today we discuss one important topics whose topics is related to spectral theorem. We now going to definition here to start from definition. Okay, we have all seen properly. So we now start. Let a complex number lambda, a complex number lambda belongs to C is called an eigenvalue is called an eigenvalue of T belongs to BH of T belongs to BH if there exists a vector if there exists a vector 0 less than equal to x belongs to H such that Tx equal to lambda x, then the vector x is called an eigenvector for T. An eigenvector for T corresponding to the eigenvalue lambda. Corresponding to the eigenvalue lambda. Lambda is an eigenvalue of T equivalently lambda is an eigenvalue of T if and only if T difference lambda I is not 1 1. Now we give some example here. Let H equal to L square. Define TH to H by T of x1, x2, x3 equal to x1, x2 y2, x3 y3 . Okay, let n belongs to n denote the standard orthonormal basis for H. Denote the standard orthonormal basis for H. Then T of En equal to 1 by n En. Hence 1 by n is a set of eigenvalues. Hence 1 by n is a set of eigenvalues of T with corresponding eigenvector En with corresponding eigenvector En with corresponding eigenvector En. Okay, then we also going to another example where A is our portion. The operator TL2 to L2 defined by T of x1, x2, x3 equal to 0, x1 by 2, x2 by 3 for all x1, x2 belongs to L2. This one is compact but has no eigenvalues. Okay, this one example of some operator. Next we discuss another example. We write some definition. Let T belongs to BH, bounded linear operator from H to H. If T equal to adjoint of T, then T is called self-adjoint. We know about that. Then T is called self-adjoint. We write it just. Okay. Then next we write here. Let M L2 01 to L201 be given by M of Ft equal to Tft for F belongs to L201 and T belongs to 01. Then M is self-adjoint. Then M is self-adjoint and has no eigenvalue. Okay. Then we're going to some proposition. We write another proposition here. Okay. Let T belongs to BH, bounded linear operator from H to H, be self-adjoint. Then first, eigenvalues of T are real. Second, Second, eigenvectors corresponding to distinct eigenvalues. Eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, then we write proof of this. We'll start proof here. Let lambda be an eigenvalue. Let lambda be an eigenvalue of t, eigenvalues of t, and x be the corresponding eigenvector, and x be the corresponding eigenvector, and x be the corresponding eigenvector. Then tx equal to lambda x. Now we erase our portion. Now lambda norm of x square equal to lambda inner product of x equal to lambda x equal to tx equal to x dx, since t is self-adjoint, equal to x lambda x equal to lambda conjugate norm of x square. Now, so lambda equal to lambda conjugate, this implies lambda be real. Okay. Next, we're going to second part. Let lambda and mu be distinct eigenvalues. Let lambda and mu be distinct eigenvalues of t and x and y be the corresponding eigenvector. Then tx equal to lambda x and ty equal to mu y. Then now mu x y equal to mu equal to x mu y equal to x dy equal to txy equal to lambda xy equal to lambda xy. Then since mu and lambda belongs to R and obviously mu not equal to lambda, so inner product of xy equal to 0. Then this implies that x perpendicular to y. Okay, so we prove this theorem also. Eigenvalues of t are real and corresponding eigenvector of distinct eigenvalues are orthogonal. We also erase this portion, and now going to another proposition. We are also going to another proposition. Here we write not proposition, we are going to one theorem. Okay, let T belongs to BH bounded linear operator from H to H. Okay, be self-adjoint. Be self-adjoint. Then what happened? Then norm of T equal to supremum of norm X equal to 1 mod of Tx. Okay, this one is the theorem we have to prove. To start now, I'll prove here, and let m equal to this one. Mark it m equal to supremum of norm inner product of Tx mod norm of X equal to 1. Now note that mod of Tx inner product less than equal to m for each x belongs to H with norm of X equal to 1. Then what happened? Then if norm of X equal to 1, then by Cauchy-Schwarz inequality, Cauchy-Schwarz inequality, Cauchy-Schwarz and Kovsky inequality norm of Tx less than equal to norm of Tx norm of X equal to norm of Tx since norm of X equal to 1. Hence m less than equal to norm T. Hence m less than equal to norm T. Okay. Then what we get? We have to prove other way. Okay, to prove a converse part, then converse part. So what we do? Let xy belongs to H, then inner product of T of x plus minus y, this equal to Tx plus minus 2 of real Txy plus Tyy. Now therefore 4 of real Txy equal to T of x plus y, here x plus y. Okay. Difference T of x minus y, here x minus y, inner product. Then this less than equal to, we write it in above. It is this portion. then this less than equal to norm of t of x plus y inner product, not norm, just mod of this plus mod of t of x minus y inner product. Then this less than equal to m of norm of x plus y square norm of x minus y square. This equal to 2m norm of x square norm of y square by parallelogram law. By parallelogram law. Okay, then what happened? Then we erase this portion and going to further discussion. Now txy equal to mod of inner product of txy expi theta for some theta belongs to R. Substituting x e to the power I theta in the above equation. We get 4 of real tx e to the power I theta e to the power minus I theta y less than equal to 2m norm of x square plus norm of y square. Okay, this implies 4 norm of txy less than equal to 2m norm of x square norm of y square. Then what happened? Then substituting y by this, substituting y by norm x by norm tx in place of y in the above equation, we get what we get. We write in above here is this portion. Four of dl not we get here norm of tx less than equal to m norm of x, hence norm of t equal to m. Okay, now we erase this portion and going to corollary. Now we write corollary here. Let T belongs to BH be self-adjoint and if Tx x equal to 0 for each x belongs to H, then t equal to 0. Now we're also going to discuss about one theorem. Okay, so we also prove our portion and also discuss this corollary t self adjoint tx x equal to 0 then t equal to 0 by this above theorem. Now we're going to write the statement of this one theorem.